Hi, everybody. This is a presentation about equilibrium and how an equilibrium can shift if something disturbs or disrupts or stresses that system and equilibrium. The principle that guides it is referred to as LeChatlier's principle. And I want to try to just illustrate very quickly with a non-chemical situation what I'm referring to when I mean like a stress or a change. Let's say we've got a seesaw at the park and we got you on one side, okay? And we've got your friend on the other side. And you guys are hanging perfectly in balance. Neither of your feet are touching the ground because you have managed to establish an equilibrium where the force on both sides is equal. Okay. Could something happen that disturbs or disrupts that equilibrium? Sure. Maybe your little brother shows up at the park and he hops on your side. Okay. If your little brother hops on your side, that's going to make your side go down and the other person's side go up, and the equilibrium has been disrupted. Can you reestablish equilibrium by shifting your positions on the seesaw? Now think about what you know from physics or general science. Sure. If the heavier side, if they move, I need to bring that up, but if they move in a little bit, and the person who is lighter moves out a little bit, then these positions are going to return to balance. I've even seen seesaws with like a couple of different notches in the middle so that you can actually change the position of the board to have one side be longer than the other. Over here with less weight, you need a longer arm. And over here with you and your brother, you have more weight, so you need a shorter arm. And you can bring this system back to where you're balancing and you're both, now all three of you actually, just kind of dangling in the air again. So how does that work with a chemical system? Okay. So remember that when a chemical system is at equilibrium, we've got a situation where the forward and reverse reactions are happening at the same rate. That doesn't mean we have equal amounts of C and D and A and B, but what it does mean is that we've reached a point where as fast as C and D are made, C and D break apart to make A and B. So we've reached a point where the ratio of C and D to A and B is remaining steady. Well, let's say that something happens and, somebody adds some D to the system. We've got some more D. That's going to make this number on the top bigger. So what needs to happen is that we need to bring the top number back down. You can't really see the yellow very well. We need to bring the top number back down and bring the bottom number up until we once again have the same ratio of CD to AB and get the same KEQ, because this is a constant. We have to arrive back at exactly the same number. Well, how can we bring C and D down? That reverse reaction can start happening faster. And that kind of makes sense in regards to collision theory. If we've increased the amount of D, C is going to run into D more often, and the reverse reaction will speed up a little bit. And the forward reaction, okay, has to slow down a little bit because we're going to make a little bit of less of C and D, okay? And so then you bring the system back to a point where CD over AB is back to the same ratio. But everything's going to shift its position. You're going to have a different amount of D, C, B, and A than you did originally. But the product of CD over AB is back to giving you the same KEQ value. We will look at a couple of reactions in class or I'm going to have some videos for you to watch if you're not in class and see this in action. But there's several things that can cause stress to a chemical reaction. You can change the concentration. Like back in that example, I increased the D, so it shifted away from the D to use it up. And if you decrease the concentration of something, it will shift towards that substance to help bring that number back up to make more of it. We're going to do this one either in class or you can watch the videos. But I'll have this equilibrium system that's kind of orangish red looking because it's a mixture of all of these things. There's some yellow ions, a clear colorless ion, and a red ion. When you have a mixture of all of those, you get a solution that's sort of orange in color. Now, if you apply a stress to that, it's going to cause a shift. For example, what if I add some solid KSCN? Now, this is going to break apart to make K+1 ions and SCN-1 ions because it's soluble in water. Now, the K ions, they're not anywhere up here in this reaction, so they're going to have no effect, and we can pretty much ignore them. But the SCN ion is on the reactant side, and if I increase it, LeChatlier's principle says if you increase the concentration of something, it'll shift away from that substance. My reaction should shift to the right and make more of the red ion, so we should see the red color, and it should shift to the right. And refer to either the demonstrations that we did in class or the video to see that actually happen. Now, another thing that I can add, and you can add lots of stuff. I mean, I could add things that have no effect on the equilibrium. If I add some NaCl to this, there's no sodium, there's no Cl. I can add salt to this. It's not going to affect this equilibrium at all. I won't see any change of color. But if I add sodium, if we add Na2HPO4, add this, what that's going to do, it's going to react with the Fe+3 and cause it to decrease. So if I decrease this by precipitating it out of the solution, because the iron phosphate is insoluble, then LeChatlier's principle said if you decrease the concentration, it should shift towards it. So I should see a shift to the left up here towards it, and I should see more of the yellow color. And you can refer to the demonstration in class to see that yellow color or to the video. Now, in this particular chemical reaction, in this equilibrium system, we've got a green ion and a blue ion and then some other things that are colorless. It's going to actually appear turquoise when you have the mixture of the blue and the green. So think about the CaCl2. It's soluble in water, so it's going to break apart and give you some calcium ions and some chloride ions. When you look in that chemical reaction, you don't see calcium anywhere, so it's going to have no effect. But the chloride, when that increases, it should shift away, so it should go to the left, and we should see more of the green ion. If I add some ethyl alcohol, that's going to mix in with the water and decrease its concentration. Again, LeChatlier's principle says it should go to the left. When it goes to the left, I should see more of the green ion. And these two will both cause a shift in that it will look more green than blue. So what's the value in this, like the practical application? Let's say in business and industry, the green ion is the one that you want to sell. Well, you want to create situations and you want to do it as cheaply as you can. Is it cheaper to add calcium chloride, or is it cheaper to add ethyl alcohol, or maybe a little of both, to cause this reaction to shift to the left and make more of that nice green ion that you are hoping to sell? Maybe it's a chemical reaction that's taking place in the body, and we need to reduce or produce more of something on the left or something on the right, and we can add chemicals that will cause the reaction to shift to create the desired effect in the body. Reversible reactions can be controlled by increasing or decreasing the concentration of something to cause the equilibrium to shift in whichever direction you desire. Now, if it's not possible to increase or decrease the concentration of something, you could also apply heat or remove heat by placing it in a cold environment. For that, you really need to know which side the heat is on. Like here, you see that this reaction produces heat. That's an endothermic, excuse me, that is not endothermic. See, even my brain sometimes goes haywire. That is an exothermic reaction when it produces heat, and we're going to have a delta H value that is negative. Some of the questions that are on WebAssign, they don't show you where the heat is in the chemical reaction. Instead, they give you the delta H value, and if it's negative, you can just go ahead and think heat on the right, or, being produced. It's after the arrow. Because in this situation, when you put this in a hot environment, it's like increasing the heat, and just like the concentration, it'll shift away from the heat. It's going to shift to the left and make more of the green ion. So maybe in industry, we want to keep this reaction really warm, and we want to add some cheap salt, get it to shift so we get lots of this green ion that we can sell it. Now, you also could have an endothermic reaction where the heat is before the arrow. If you put that in a warm environment, that one's going to shift to the right because it's going to shift away from the heat. Now, in this exothermic reaction, if we put it in something cold, like an ice bath, okay, adding it to an ice bath instead of increasing the heat, that's going to remove heat. Just like with concentration, it's going to shift towards whatever you remove. So if I put it in an ice bath, it's going to shift to the right, which it's going to make then more of this blue ion. And if you watch the video or remember the demo in class, you're going to see a lot more of the blue ion being produced. Again, if this was endothermic and the heat was on the left, as if it's endothermic, delta H will be positive and heat would be, over here. If you put it in a cold environment, then it would shift towards the heat on the left. So you got to know which side the heat is on so that you know which way it changes. And remember, the delta H value of an endothermic is going to be positive, whereas the delta H value of an exothermic reaction is going to be negative. So changes in temperature. If the temperature increases, it'll shift away from the side with the heat. Which side has the heat? If delta H is positive, the heat's before the arrow. If delta H is negative, the heat is after the arrow. If the reaction's endothermic, it's before the arrow, the heat. If the reaction's exothermic, the heat is after the arrow. And then if you decrease the temperature, it's going to shift towards whichever side has the heat. Now, the last stress that we're going to talk about, changing volume, really just applies to gases. Because when you change the volume of the container, okay, you change the pressure. So if the volume decreases, remember the pressure will increase. And I think some of the problems on WebAssign even just maybe directly say you increase the pressure. Anytime you increase the pressure, either by decreasing the volume or directly increasing the pressure, it's going to shift to make less moles of gas, because less moles of gas will help to bring the pressure back down. If you increase the volume, that's going to cause the pressure to go down, and it's going to try to make more moles of gas to bring the pressure back up. So it's going to shift in whichever direction gives you more moles of gas. I know when I was in high school, I remember kind of trying to memorize this and saying, like, well, if the volume decreases, there's not as much room. I need less moles of gas. And if the volume increases, there's way more room for the gas. So it'll make more of the gas. And so maybe that's one way that you could potentially remember it. Here's an example. I could not demonstrate this because I don't have any way to capture the gases. But let's say in this example, we decrease the volume of the container in which this reaction is happening. Okay. On the, that'll show up very good. On the left side, do you see that I have 4 moles of gas? Whereas on the right side, I only have 2 moles of gas. Because over here it's 1 and 3, over here it's just 1 and 1. So if I decrease the volume, it's going to shift to make less moles of gas. This is going to shift to the right. If I'm trying to make CH4, I want to conduct this reaction in as small of a container as I can to try to get it to make more CH4 in my mixture. Here's another one. In this one, we're increasing the volume. So again, you really have to inspect, okay, how many moles of gas do I have? On the left, I have 4 moles of gas. We're not counting the ion or the iron because it's a solid. On the right, this is a solid, so I have 4 moles of gas again. If it's equal, changing the container's volume is not going to create a shift in the equilibrium. I'm still going to have exactly the same amounts before and after because they both have 4 moles of gas, and it's not going to favor one side or the other. Now, if they had a different number of gas, increasing the volume, it would shift towards making more moles. Some other things that do not shift the equilibrium, adding a catalyst. Now, adding a catalyst might make it reach equilibrium faster, but it's not going to change the amounts or the identity of what is produced. So I hope that that helps you in predicting the shifts when stresses happen. And, you know, just think of the seesaw when the kid jumps on the one side, they had to make their arm shorter because they had more weight. And the person on the other side of the seesaw had to scooch back and make their arm longer because they had less weight. So a chemical reaction is the same. If you change something about it and disturb the equilibrium, it has to shift. And it can reestablish an equilibrium, but you'll have new amounts of your reactants and products. Their ratios are still going to be equal to products over reactants, giving you the same K, but you might have now different amounts of each of the items. So hopefully that helps. And you can now predict equilibrium using LeChatlier's principle.